Hello. My name is Liam. Dr. O'Sullivan has asked me to introduce the lesson today because I have a British accent and everything sounds more impressive with a British accent. Today's lesson is on atomic mass. If you look above my shoulder you see the symbols for several elements. Take sodium, for example. The smaller of the two numbers, 11, is the atomic number. The larger number, 22.989, is the atomic mass. Your job today is to learn where that number comes from. Well, I'm now going to turn it over to Dr. O'Sullivan. Enjoy your lesson on atomic mass.
Here's the information we typically get for the element magnesium from the periodic table. As Liam said, the larger of the two numbers, atomic mass, is the focus of this lesson. Let's say we have some magnesium ribbon which looks like what you see here. Let's say we took a piece of that ribbon and then magnified a tiny section of it many times, so much so that we could actually see the atoms of magnesium. We would find that although every atom is magnesium, they're all not quite identical. They all do have an atomic number of 12. But imagine the first one represents an atom with a mass number of 24, the second a mass number of 25, and finally the last one a mass number of 26. Recall these atoms with the same atomic number but different mass numbers are called isotopes of each other. So our job in this lesson is to determine what the connection is between the mass numbers of individual isotopes of magnesium and the atomic mass of magnesium. They definitely seem to be related. After all the numbers are very close to each other. Let's dig a little deeper. Now, even though these are called mass numbers, they are not masses. Recall mass numbers determined by adding the protons plus the neutrons. Well, when you add how many particles you have, you don't end up with a mass, you end up with, well, how many particles you have. Here, on the other hand, you now see the actual mass of each atom of each of these isotopes. Notice the mass of magnesium-24 is very close to 24, but not exactly 24. The mass of magnesium-25 is very close to 25, but not exactly. Same for magnesium-26. Ask in class if you want to know why the actual mass is so close to, yet not the same as the mass number. One of the reasons relates to something we've covered. For now, what we do want to focus on is that none of these actual masses are equal to the atomic mass 24.31. So all this brings us to the main point, the definition of atomic mass. We need to consider two things. One, the actual masses of the isotopes of magnesium here, and the percent abundance of each of these isotopes here. By percent abundance, we mean that of all the magnesium atoms in the world that are naturally occurring, 78.99% of them are the isotope magnesium-24. 10% of them are magnesium-25, and so on. Notice there are far more magnesium-24 atoms in the world than the other isotopes. So now I'd like you to propose a definition of atomic mass. In other words, how is this 24.31 determined? Stop the video now and write your definition. Okay, here it is. The most important thing is that the atomic mass is the average. Specifically, it's the weighted average of the masses of all naturally occurring isotopes of an element. It's important to know it's a weighted average. If I just asked you what's the average of these three numbers, since they're all very close to these whole numbers, the answer would be almost exactly 25. But the atomic mass is 24.31, much closer to 24 than 25. This is because there are many more magnesium-24 atoms in the world than the other isotopes of magnesium. If you want to see the actual calculation, it looks something like this. Notice we take the mass of each isotope, like this one, and multiply by its fractional abundance, and then do the same for the other isotopes and then add them up. That gives us our 24.31. Now, although you should understand this calculation, the most important thing for this lesson is to understand atomic mass conceptually. If we remember it's a weighted average, it allows us to make a decent prediction what the most abundant isotope of an element is. For example, if we didn't have the percent abundances shown here, and we do know the atomic mass, we could predict the most abundant isotope is magnesium-24. Just pick the whole number closest to the atomic mass. Just like if you took a test in a class of 20 people, and the teacher told you the average was 89.8, and further revealed there were only two scores among the 20 students, 90 and 89. With that information, you know for sure that more people scored 90 than 89 because the average is closer to 90. Let's apply that idea to the next question. Consider the four elements you see here. We'll estimate the most abundant isotope of all four, but let's do the first one together, carbon. Since the atomic mass is 12.01, we can predict the most abundant isotope is carbon-12. Just pick the whole number closest to the atomic mass. That method won't always give the correct answer, and we'll see why in a moment, but it usually will. Stop the video now and do the last three. Our answers are boron 11, because 11 is the whole number closest to 10.81, calcium 40, and this next one is not bromine 80. Yes, 80 is the closest whole number to 79.90, but it turns out that the isotope bromine 80 doesn't occur naturally. How would you have known that? You wouldn't. And if this were an actual test, I wouldn't have expected you to know it. But if I give you a hint like the following question, you should be able to predict the answer. Here it is. If there are two naturally occurring isotopes of bromine, and bromine 80 is not one of them, predict what those two isotopes could be and their relative abundances. The one hint I'll give is that it's common for all isotope mass numbers to be close to the atomic mass. For example, since the atomic mass is 79.90, you can be certain that the two answers are really close to 79.9 and not say bromine 45 or bromine 100. Stop the video now and write down your answers. Bromine exists as bromine 79 and bromine 81, with bromine 79 being slightly more abundant. Let's break that down. First, as I said, mass numbers of elements tend to be very close to the atomic mass. So if the atomic mass of bromine is 79.90, any reasonable mass number will be a whole number really close to 79.9. Second, we could predict that bromine 79 is slightly greater than 50% and bromine 81 slightly less because the average mass, which is really a weighted average, 79.90, is closer to 79 than to 81, but not much. Just like if you had only two test scores, 79 and 81, and the average on the test was below 80, you know for certain more people scored 79 than 81. Well, that's it for atomic mass. Thanks for listening, and see you next time.